Good day and welcome to Math 111H Calculus 1 Honors, The Joys of X. Today we're going to discuss hyperbolic trigonometric functions. We defined some new functions based on old ones, exponential functions we'll find out, because they have some nice properties that can make doing calculus with them easier. We call them hyperbolic functions because the equation of a hyperbola, x squared minus y squared equals 1, has a similar look to cos squared minus sin squared equals 1. That is, hyperbolic cosine squared minus hyperbolic sine squared of x equals 1. So here are some definitions. We define sinh of x, or the hyperbolic sine of x, to be e to the x minus e to the negative x over 2. And that's simply a definition. We'll find out some things about it later. We define cos x, the hyperbolic cosine of x, to be e to the x plus e to the negative x over 2. So sinh and cos have a similar look. They only differ by this negative sign. One can analyze them and notice that sinh x is odd, just like sine is, and cos x is even, just like cosine is. Okay, we define tanh of x, the hyperbolic tangent of x, to be sinh x over cos x, so very similar to tangent. Sech of x is equal to 1 over cos of x, just like secant is 1 over cosine. Similarly, coth of x, the hyperbolic cotangent of x, is cos over sinh, just like cosine over sine for cotangent. And the hyperbolic cosecant of x is 1 over the hyperbolic sine of x. Let's take a look at some of the implications. Let's look at sinh of x is e to the x minus e to the negative x over 2, and let's take a look at its derivative. The derivative of sinh of x, therefore, well, the derivative of e to the x is e to the x. The derivative of minus e to the minus x, well, that's going to give you a plus e to the minus x. And we have the 2 on the bottom staying there. And that's just the definition of the hyperbolic cosine. So the derivative of hyperbolic sine is hyperbolic cosine. Similarly, we can work out the derivative of hyperbolic cosine of x, and we find that that's simply the hyperbolic sine of x. So it's even easier than the derivative of sine being cosine and the derivative of cosine being minus sine. Here, the derivative of sinh is cos, the derivative of cos is sinh. And we can find the derivative of each of the other hyperbolic functions we defined using these derivatives, the derivative of sinh and cos, along with the quotient rule. We leave it up to the viewer to work those out. We can also find the derivative of the inverse sinh of x, the inverse hyperbolic sine of a function, just like, and it's exactly the same as we did previously in using implicit differentiation to find the derivative of the inverse sine of x. So implicit differentiation can be applied to find the derivatives of the inverse hyperbolic trigonometric functions now. And we do it exactly as we did earlier. We have y is the inverse hyperbolic sine of x. We operate on both sides with the hyperbolic sine, giving us sinh y equals x. Treat y as a function of x. The derivative on the left, derivative of sinh is cos, so we have cos y times dy dx is 1, giving us dy dx is 1 over cos of y. Well, what's cos of y? We can notice, if we work out the algebra, that cos squared of y minus sinh squared of y is equal to 1. As we noted earlier, that's why these are called hyperbolic functions. Bringing the sinh squared over to the other side, we have cos squared of y is 1 plus sinh squared of y. And so cos of y is simply the square root of 1 plus sinh squared of y. We plug in sinh of y is equal to x, so we have the derivative of the inverse hyperbolic sine of x is 1 over the square root of 1 plus x squared. So that's one of the things that turns out to be easier using these inverse hyperbolic functions, that the derivative of inverse hyperbolic sine is 1 over the square root of 1 plus x squared. Similarly, we can work it out for the inverse hyperbolic cosine. The derivative of the inverse hyperbolic cosine of x is 1 over the square root of x squared minus 1. And the derivative of the inverse hyperbolic tangent of x works out to be 1 over 1 minus x squared. Turns out that because we defined the hyperbolic functions to be just functions based on functions that we know, turns out that there's another way to represent them. We could represent the inverse hyperbolic sine of x in a much messier way. And again, we operate on both sides with sinh. So we get sinh of y is equal to x. We plug in the definition of sinh, which is e to the y minus e to the minus y over 2. multiply both sides by 2. Let's bring the 2x over to the left. Then we multiply both sides by e to the y, giving us e to the 2y minus 2x e to the y minus 1 equals 0. If we let u equal e to the y, this equation becomes u squared minus 2x times u minus 1, which is just a quadratic equation. We can use the quadratic formula to solve for u. U is equal to minus negative 2x, so 2x plus or minus square root of b squared minus 4ac. This is a typo. There should not be a squared over here. Okay, u is equal to e to the y. Just leave the right-hand side the same, except I fixed the typo. Okay, we can then notice that e to a power has to be positive. So the negative sign doesn't make sense. So we have e to the y is 2x plus the square root of 4x squared plus 4 over 2. Dividing out the 2, we get x plus square root of x squared plus 1. Taking logs of both sides, you get y is equal to the natural log of x plus the square root of x squared plus 1. That's a mouthful, and that's maybe one of the reasons that we like to name it y equals inverse hyperbolic sine of x, because that's a nicer way to look at it than this log. Okay, let's take a moment for some math culture. There were 2 NJIT students who were piloting a plane when they discovered that they must make an emergency landing. Luckily enough, there's a nearby unused airstrip, so they decide to land there. As they fly over it, one of the NJIT students said to the other, "That's an awfully short runway. I don't know if we can land on it." The other student points out, well, there's no choice, so they have to try. They bring the plane in as slowly as possible, touching the wheels right at the beginning of the runway, and immediately they hit the brakes. The plane slides to a halt with the front wheels hanging off the runway's end. One of the students turns to the other and says, "We made it. Whew. But this has got to be the shortest runway I have ever seen." The other turns to him and says, "Yeah, but it must be at least 2 miles wide." Thank you for joining us today. Have a great day, and may the power of math be with you.